All right, 3.7. We're going to call 3.7 chemical change. So we want to represent a chemical, or we want to look at what a chemical change is first. And so a quick definition: a chemical change is any change that results in the formation of a new chemical substance. So in essence, what we do is we take original bonds and we break them, and then reform with other elements to possibly make new compounds and new bonds. Some examples would be like rusting of a substance, or the explosion of material, or just digestion of food. I've got the picture of the apple here because rotting or the browning of the apple is also another good example of a chemical change that's occurring. The right side of the apple has been treated with an acid, and so that keeps it from actually decomposing. The left side of the apple has been left untreated, and so it browns like a typical apple. The browning that you see going on is an example of a chemical change. So what isn't a chemical change? If something is changing or is being altered, but it's not being altered chemically, then we could say that it's being altered physically. That's any change that does not result in the change of the identity of the particular chemical. So some simple examples are like freezing or melting or cutting of a substance. In the case of freezing, you take some water and you freeze it, it turns into ice. It can obviously be thawed and turned back into liquid water. Cutting of a material, so if you're taking some aluminum foil and you're cutting it in half, obviously both halves remain aluminum foil. And this is just a nice depiction of the process of a phase change, which is not a physical change, or not a chemical change, it's a physical change. So taking liquid water and turning that into solid water or ice. Also, on the right side, it shows an actual chemical change, which, as you can see, we're altering the molecules. So we have the two molecules on the left side of the yields arrow right here. Those are the hydrogen peroxide molecules, and you'll notice that on the right side of the yields arrow, they actually change their structure. So we have water molecules there and an oxygen molecule there. So we have this complete change of the chemical in itself. I want to take a look at a change that we actually did in class that was a physical change, and we modeled this on the whiteboard. We talked about why the silver nitrate that we used in the lab is shown as being separated in the molecular level diagram that was on the lab handout. And so we have silver nitrate, and this is the solid silver nitrate that comes from the chemical company. And I'm going to put an S down here. If you notice this S right there, that denotes the phase of the substance. So we're saying the silver nitrate is a solid, so it looks like a crystal. And to that solid, we add a little bit of water. And as we showed on the whiteboards, what that water does is it acts as the butcher. It's an ionic butcher, and it cuts apart the ions that are involved in the compound. And so instead of having silver nitrate solid, we actually get random silver ions. They have a 1+ oxidation number. And then we also get nitrate ions. And those nitrate ions have a 1- oxidation number. Now, both of these ions are said to be in solution. And so the way that we denote that, the way we tell the reader that, is by using a subscript that is labeled AQ. AQ means aqueous. And if something is aqueous, that means that it's being dissolved in water. Now, why is this not a chemical change? Well, quite simply, all we have to do is heat up the resultant solution, and we'll get the original silver nitrate back. So it's easily reversible. So even though this looks like a chemical reaction, the way that I've drawn it, it isn't. It's a physical change. Okay, so we could almost call it like a physical reaction. But it's a very common one because very oftentimes in chemistry we take solid substances, we dissolve them in water, because when they're dissolved into water they actually react quicker, so it speeds up reaction times. Okay, so let's focus again on those chemical changes. So representing chemical change, how do we do that? So first of all, we use a chemical equation to do this, and I've kind of shown that with the physical change of silver nitrate, but we'll go more into depth right now. So a chemical equation is just simply a symbolic representation of a chemical change, and we're going to take a look at one of those right now. So let's look at this process. We're going to take some iron metal, some random iron metal, and we're going to place it into a solution of copper chloride to form iron 3 chloride and copper metal. Now what you're going to be asked to do as the chemistry student is to take that verbal sentence and actually write out a chemical equation. Okay? So iron metal. Well, iron is just Fe from the periodic table. I'm going to make that a little bit smaller. And if it's a metal, it's going to be a solid. We want to denote what the phase is of that material. Okay? Copper, 2 chloride. Okay, copper 2 chloride, Cu, Cl2. See, this is where your writing of your nomenclature comes into play. Cu, CO2, that's copper 2 chloride. And it says it's a solution of copper 2 chloride. So we're actually just going to put the AQ right after that entire compound. If you remember on the previous slide, we broke it up into ions. We showed the separate copper ions, the separate silver ions and the nitrate ions. But we can also show that as a combined entity, so that's what we're doing right now. So the AQ is telling us that this entire material has been dissolved into water. Okay, so we've got that side of the equation. And then we have this phrase right here. It says to form. So the phrase to form is kind of indicating that we are now producing something new. And the new stuff is iron 3 chloride, which is written like this, FeCl3, and copper metal. And is usually a good place for a plus sign. And copper metal, Cu. Okay? Now the iron chloride, and I don't say this in the sentence, but I should say this, the iron chloride in this particular reaction would be a solution. So we want to draw AQ, and I want to draw that right where it should be. FeCl3 with an AQ after it. And then copper metal, so there's that word metal again, so the copper itself is going to be a solid. Okay, so there is your chemical equation. And what we have to kind of parse out here, this side of the equation, that side is going to be known as, quite simply, the reactant side. Okay, and the right side of the equation, this side over here, that side is going to be known as the product side. There's the product side right there. Okay. Now, some of you may look at that equation. You've probably had experience before with chemical equations and think, there's something missing there yet. We haven't balanced the equation, which you may have done in a previous class. We'll get to that in a second. Okay. So let's move on. So this whole balancing process, why do we do it? Well, we do it because we have to observe this very important law in chemistry, and it's called the law of conservation of mass. It quite simply says that mass can't be created or destroyed. If you got some iron atoms, you can't just make them disappear into nothingness. They're always going to be there, or at least until you do some type of nuclear process, but then the matter that used to make them up will either be there or be turned into energy. But for our purposes, we just have to know that if we start with 10 grams of stuff, we got to be able to account for that 10 grams of stuff a little bit later on. So to follow the law of conservation of mass, equations, chemical equations themselves, must be balanced. And so we're going to draw another chemical equation here, and it's going to be the combustion of methane. We do the combustion of methane a lot in this class because the combustion of methane is what we do with our Bunsen burners when we turn our Bunsen burners on. The gas coming out of there is methane. Methane is a gas, so we're going to actually abbreviate that with a G, and that combines with oxygen. Oxygen gas. And the result of this combination is going to be water. So H2O, we're going to call it a gas for now. And carbon dioxide, CO2. We're also going to call that a gas. Okay? Now, knowing what you know about balancing chemical equations, this particular equation right now, as written, is not balanced. As you'll notice that we've got 4 hydrogens here on the left side of my yield zero, but only 2 on this side. So what we'll need to do first is make sure that we have those hydrogens balanced. And so I'm going to go ahead and put a 2 in front of the water. And what that says is, via this reaction, I actually have 2 water molecules that are produced for every one methane molecule and 1 oxygen molecule. Okay, now let's recheck. Okay, well, now we have 4 hydrogens here because we've the 2 times the 2 and 4 on that side. So hydrogen's great, but as you'll notice, oxygen's not quite balanced yet. If you look here, you've got 2 oxygen atoms. Here you've got 2 more oxygen atoms for a total of 4, but here you've only got 2. So a 2 coefficient in front of the oxygen there is going to be helpful. And that's going to give you a balanced chemical equation. So if we want to take a look at what that looks like on the actual molecular level, we've got 1 methane molecule, so 1 carbon and 4 hydrogens around it. And then we've got 2 oxygen molecules right here for a total of 4 oxygen atoms. And on the right side, you'll notice that all of the oxygen atoms are accounted for. And you'll also notice that all of the hydrogens are accounted for. There's 2 there, plus another 2, and there's 4. There's 1 hiding right back there, 2, 3, 4. And then finally, the easiest is obviously the carbon atom. There's 1 carbon atom and 1 carbon atom right there. So balancing allows us to follow the law of conservation of mass. Now what we'll notice a little bit later on is that to talk about 1 molecule of methane and 1 molecule of carbon dioxide is not really helpful at all. So later on we're going to talk the fact that we usually talk in moles. So like 1 mole of methane will give us 1 mole of carbon dioxide. Now one thing that you may have noticed is oxygen. Why is oxygen O2? And that's something that we have to address right now. That's got something to do with what we call the Hofbrinkel issue. So Hofbrinkel. Hofbrinkel, what's that stand for? Well, it stands for the elements that are defined as being diatomic. So these elements, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, are all what we call diatomic. Diatomic means that these elements are going to always travel in pairs. And most often, these things are going to be gases. So for example, if we take a look at hydrogen gas in its combination with oxygen gas to form water, well, what does that look like? Well, most of us, if we would just read this right now, we would say, okay, hydrogen gas plus oxygen gas gives us water, if we cool it down in the liquid state. Okay? However, hydrogen never floats around alone. I'm going to tell you why this is in class. Oxygen also never floats around alone. We'll show this why this is in class. It always has another hydrogen that it's hanging out with. And so instead of just writing H, we actually write H2. And we write O2, still gases. Okay? And that gives us the correct chemical equation. We would then have to balance it with a 2 here and a 2 there. And so every single one of these elements up here, again, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine, followed the same idea. So if we ever see chlorine gas, we're going to write it like this. Now, one thing that you're going to be really eager to do is you're going to see something like, hydrogen chloride. You're going to write it like this. You're going to write it like HCl, and you're going to say, oh, they both need 2's after them because they're diatomic. The only time when you have to write that 2 is when the chlorine is all by itself, or when the oxygen is all by itself. Okay, so that's 3.7.